Welcome back to the video on ATC. And in the previous video we had gone through how to convert a finite automata into regular expression. In this video we will understand how to convert regular expression to a finite automata, and also we will go through Kleene's closure algorithm and also some aspects of state elimination method that we had missed in the previous video. So in this video we will be solving two questions on these topics. So first question we will be taking up is 0 plus 1 whole star 1 0. So now, how do we convert this regular expression into a finite automata? First step is to find which is the basic step, basic component of this expression. They are 0 and another is 1, right? So how do we find a finite automata for this? It will be very simple. This will be the finite automata to accept only the symbol 0. Similarly, for 1 it will be this, right? Now we have, in the next step we will just increase the complexity of the expression a little bit. So we have 0 plus 1 over here. So now let us try to convert 0 plus 1 into the automata, finite automata. So we will just take that basic automata over here and combine both of them so that we get the required automata, and we combine these automata with the help of epsilon transitions. So as in the previous video we understood that when do we use epsilon transition? We use epsilon transition when we do not need any symbol to make the transition from one state to another state, right? So here we must have either 0 as the symbol or 1 as the symbol. So this is how we do the conversion of this regular expression into the finite automata. Now another expression in the given expression is 1 0, right? So now let us try to convert this expression into a finite automata using the basic finite automata that we have created for 0 and 1. So in this expression we have 1 in the beginning. Since there is dot operator in between these symbol, we'll have to do a series connection here. Since there is a plus operator here, we have combined the basic finite automata of 0 and 1 in parallel, but here we will do it in series. So first one is with the symbol 1, and we have another automata that is 0. So we make an epsilon transition in between these two finite automata. Now we'll have to combine these two finite automata and make the final expression. Before that we have 0 plus 1 whole star, right? So how do we make 0 plus 1 whole star? So we just have to take the 0 plus 1 finite automata. So the 0 plus 1 finite automata is epsilon transitions. So this is the finite automata for the expression 0 plus 1. How do we add the whole star over here? We have to just take this back to the initial state with the epsilon transition. We must have to just loop back, right? And then we have to connect this automata, the automata for the expression 1 0, with this automata, so that we get the final automata. So what is the automata here? This, and we connect these two finite automata with the epsilon transition, right? Now this is the final finite automata that we require, and this will fetch you. So this finite automata will fetch you the marks for converting from a regular expression to a finite automata. Further, let us try to optimize this finite automata and then convert that finite automata to regular expression, back to regular expression, using Kleene's closure algorithm, so that we can understand Kleene's closure algorithm also with this example itself. So we have q1 as the initial state. Here we can observe that from this state we are looping back to the final state like this, right? So we can simply write epsilon 0 epsilon and again epsilon, right? As in how we did in state elimination method, right? But here we have epsilon 0 epsilon epsilon. And what is the purpose of having epsilon? The epsilon means that we do not need any symbol to make the transition from one state to another state, but we already have a symbol over here, right? That is 0. So we can simply ignore the epsilon over here. And similarly we also have this path as well, so we'll just write 0 comma 1 here. And we can also observe that since this states, this and this states are connected with the epsilon transition, these two states are logically same, and also this state is also connected to this state, the previous state, this state, with an epsilon transition. So these two states as well are same, right? So we can consider this and this state as same, and we can make this transition, this transition, that is the transition with the symbol 1, from here to the next state q2. And this epsilon transition can be ignored because there is no conflicts here, so we can just write this transition. So this is the minimized finite automata. Well, we can also just land upon this minimized finite automata from the expression itself with intuition, but this is the prescribed method to find the finite automata. So now let us try to apply Kleene's closure algorithm on this finite automata and convert this back into regular expression. So whenever you apply Kleene's closure algorithm, just try to make sure that all states are reachable. Suppose here, instead of this transition, there is this transition, suppose, then q2 is not reachable from the initial state q1. Since it is not reachable, this will not play any role in this finite automata. So we can just eliminate that state and simply write this transition. But here we do have a transition over here, right? So we'll have to consider all the states over here. Now what we have to find out is the path from state 1 to state 3 through all the three states. So I hope you understood the notation over here. This 1 is the initial state, 3 is the final state, and this 3 over here are the nodes through which the path goes, right? So now let us do this. What does Kleene's closure algorithm state? Now let us just state the induction step over here, and we'll state the basis step of the Kleene's closure algorithm when required. So the induction step formula is that Rij, that is root from I to j node with through k nodes, is Rij to the power k minus 1, and we have we'll have all the nodes to the power k minus 1 in the formula. So this is the formula, and this is the trick to remember this formula. We just have to place I and j at the dead complete ends and fill in k in between here. So this is how is the induction formula for the Kleene's closure algorithm. So now let us apply the Kleene's closure algorithm on this. We need to find R13 through all the three nodes, right? So R13 here k is 3, so 3 minus 1 is 2, and we have I as 1 and j as 3. So again here we have 2 whole star and r to the power 2, and we'll just have to fill in the I, k and j placeholders here. So I is 1, k is 2, again k is 2, and finally j is 3, right? Now do we know the term R13 to the power 2 or R12 to the power 2 and or all of these terms? We don't know. So we'll have to first find those terms. So now let us find those terms first. So this is why we call this induction formula, right? We'll have to induce the formulas until we find a basic expression for the terms, and then we'll have to substitute in the backwards order, right? So we'll just write Yes. So this will be 1 2 2 2 2 3. Oh, did we do a mistake over here? This is k, right? We'll have to fill in the value of k. K here is 3, not k minus 1 is what we have to. It is not k minus 1 here, it's k, right? So we'll have to write 3 over here. And similarly here we have written 2 in the place of k. So this term is defined, this term is also defined. Now we'll have to define this term r33 to the power 2. So now this term is also defined, this term is also defined. Is this defined? No, right? Now we step into defining the terms with the superscript 1. So r13 to the power 1. So this will be 0 and here the value of k minus 1 is 0. So let's fill in that. And now we'll fill in I and k and j values. K is 1 1 1 and 1 3. Now we have that, we have to do that. We have to define the term r12 to the power 1. So r12 to the power 0 plus r now we'll define r22 what is r22 to the power 1. And 2 1 1 1 and 1 2. Now what is r23? So r23 to the power 1 is r23 to the power 0 plus r23, no, let's fill in this first so that we don't get confused. 1 1 1 1 3. So next term is r33 r32 and now R22 is already defined and R23 is also defined. Now we'll have to define with the superscript 0. So now we have, okay, so what is R13 to the power 0? R123 to the power 0. Is there any direct edge from 1 to 3? No, right? So it's 5. So it will be difficult for us to simply find the edge in the figure. Instead, what we can do is write a transition table for this. So what is Q1, Q2, Q3? So what happens when Q1 gets 0? It stays in Q1, right? So Q1, and when it gets 1, it stays in Q1 as well. It can go to Q2. So Q2, when it gets 0, it goes to Q3, and Q2 when gets 1 has nowhere to go, and when Q3 gets 0 or 1, it has nowhere to go, right? So let's just have 5. Okay, now let me, oh gosh. Okay, now let me take this transition table down where I need it. Okay, now let us simply fill in the values directly here. So is there any direct edge from 1 to 3? So here's 1. So do we have any edge here? Do we have Q3 in this row? No, right? So it will be 5. Do we have any edge from 1 to 1 again? Yes, there's 0. So when such a case is encountered, like when we have a loop, or where I and j are equal, like this case 1 1, right? We'll have to see if there is an edge for self loop. If there is one, we'll have to write a plus epsilon, because to stay in the same state we would not need any symbol as well, right? But also we have a symbol over here, so we should write a plus epsilon. And if there is no symbol over here and we have I is equal to j, then we have to simply write epsilon in that place. And this is the basis step of the Kleene's closure algorithm. So let me clearly define state what are the basis step for the Kleene's closure algorithm. So when we find such a situation, then Rii to the power 0 will be a plus epsilon, and when we find this situation where there is no self loop at all, then it will be epsilon. And suppose there is this situation, then it will be Rij power 0 only a, right? And suppose there are two edges over here, b, then it will be a plus b and also in the case of I is equal to j, suppose there is one edge a and also we have another edge with b, then we'll have to simply add b as well in this expression. So and this can also be represented like this. So now let us go back. Right, so now let us find the terms with superscript 1 by substituting the terms with superscript 0 over here. So from 1 to 3, do we have any edge over here? No, right? So then this will be 5. And from 1 to 1, do we have any edge? There is, right? 0 and 1, both we can have both the edges. So we have 0 plus 1 plus epsilon, and we also have 0 plus 1 plus epsilon over here, star, and we have 1 to 3, there is nothing, so this will be 5 again. So 5 concatenated with anything will be 5 again, and applying plus operator with 5 would end up with the other term. Okay, right? So this will be the rule. So we end up with 5 for this. So 1 to 2, we have one edge, right? That is with 1. So now this will be 1. So we know that r11 to the power 0 is 0 plus 1 plus epsilon, and again we have r11 plus 1 plus epsilon whole star, and what is 1 to 2? Do we have? Yes. So again, yeah, 1 to 2. So it is 1. And here, if you closely observe, we have 0 plus 1 plus epsilon. Epsilon means that we need no symbol at all, right? It is empty string. So can we produce that empty string from this expression? Yes, right? If epsilon if this star is 0, then we end up with epsilon again, right? So we can simply ignore epsilon over here. Before that, we also have and also we have a single term over here, 0 plus 1 plus epsilon, and this expression also contains epsilon. That means this expression can also be an empty string. So can we produce that simply from 0 plus 1 to the power star? Can we produce all these expression, that is empty string and 0 or 1 or 0 to the power something like 3 or and 1 to the power 3, like that? Yes, right? So we can simply write 1 plus 0 plus 1 whole star and 1. And here also, can we simply produce 1 from 0 plus 1 whole star 1? Yes, right? When this star is 0, we end up with only 1. So we can simply write 0 plus 1 whole star 1. So this will be the final expression for this. Now let us move further, and also we'll have this table a bit below. Can cover most of the things, right? So from 2 to 2, do we have any edge? No, right? So since 2 is equal to 2, that is I is equal to j, we'll have to write epsilon. From 2 to 1, do we have any edge? No. So that is phi. 1 to 1 we have that, but concatenated with phi would end up with phi again, but we'll have to fill that up. So 1 to 2 we have 1. Anyway, that ends with epsilon, right? Now 2 to 3, do we have any edge? Yes, we have 0. So 2 to 1, no, nothing. So phi 1 1 is 0 plus 1 plus epsilon star, and we have 1 2 3, no, we don't have anything. That's phi again, so 0. What is 3 to 3? 3 to 3, there is no edge, so we'll have to write epsilon since I is equal to j. In this case 3 to 1, we don't have anything, no edge, so it ends up to be phi again. And what is 1 to 3, do we have any? No, again. So this is epsilon. What is 3 2? Do we have an edge from 3 to? No, so it's phi. From 3 to 1, nothing. Phi 1 to 1 is 0 plus 1 plus epsilon, as we previously saw. And what is 1 to 2? We have an edge 1, but it doesn't reflect anything. Now let us fill in the terms with superscript 1 to find the terms with superscript 2. So do we have r13 to the power 1? Yes, it's phi. What's r12 to the power 1? It is 0 plus 1 whole star 1. And what is r22? It's epsilon star. What is r23? 0. So as we saw previously, we have epsilon here and there is concatenation over here, that is we have other symbols as well, so we can simply ignore this epsilon, and we have 5 over here. So we saw the rule which leads to the answer 0 plus 1 whole star 1 0. Oh, is this the expression we created the finite automata from? Right, we have already ended up with the phi with the regular expression we require. So let's see what happens. We have this r33 is epsilon, and what is r32? r32 is phi. So phi with anything is phi again. Let's fill. What is r23 to the power 1? It's 0, so we end up with epsilon. Now we'll have to just substitute these values here. What is r13? 0 plus 1 whole star 1 0. Again we have r13 to the power 2, so 0 plus 1 whole star 1 0. 1 0. And what is r33? We have epsilon star, again we have epsilon. So as we previously saw, we end up with 0 plus 1 whole star 1 0. Since we have epsilon here and we have other symbols as well, with the concatenation between them, we can just ignore the epsilons here, and the same term a plus a would be again, we would end up with a again, right? Similarly, we just end up with this expression So is this the expression we created the finite automata? Yes, right? So we have done everything right until now. Now let us try another problem that will give us full understanding with these concepts. So let's take another expression, that is 0 1 plus 1 star 0. So previously we have seen what are the finite automata for the basic symbols 0 and 1, right? Now let us not just have that again. We'll jump into creating the finite automata. So we have 0, and we also have we also have 1 over here with concatenation here. So we'll have to uh, combine the automatas of 0 and 1 in series, and again, so this is for 0 1, right? Now let us also have an automata for 1 star 0. So what happens with 1 star 0 is we have an automata for 1, and this again goes back so that we can have 1 star, and we'll also have what do we have, 0 as the final symbol over here. So we have these two finite automatas for two expressions over here. We'll have to combine these two finite automata. Since there is plus, we'll have to combine these two parallelly. So let us have both the automatas over here. Let's write both the automatas here. So first one is to have, what is that, 0 1, right? First automata is to have 0 epsilon and 1, and second automata is to have 1 over here. This goes back. We also have, yeah, here we have epsilon transition. So here there is 0, and finally we'll have to combine these two finite automata with epsilon transitions also at the end, which leads us to the final state. So this is the required finite automata. So like we did in the previous automata, let's just minimize this so that we can apply state elimination method for this, and we can have complete understanding on how to you know how to do the state elimination method completely. So we have the initial state q1 over here. Since this is epsilon transition over here, can we simply understand that both of these are same? Can we do that? We can do, probably. So let us write q2, and again here we have epsilon transition, so we can simply consider these two as same states. So 1, and we have these two states with epsilon transition, so we'll just consider these two states as same, so Q3 is the final state over here. And here, can we assume these two states as same? No, right? Because suppose we consider these two states as same, then we'll have to well, that will lead to a different expression altogether, right? So uh, we'll retain this epsilon transition over here, so we'll have Q4 here, and again we have 1 over here, because you see there's a loop here, so we can simply eliminate this state and we can have a loop, and finally we get 0 over here for this, and this is an epsilon transition, so we can simply consider these two states as well as 0. Now let me make it clear why should we retain this epsilon transition over in this case. Suppose we don't retain the epsilon transition here, then Q2, then this will be the finite automata, right? This will happen to be the finite automata. But what does this expression lead to? We have 1 star, this loop, and then we have 0 and we have 1, but we simply need 0 1 over here, as you can see in the expression over here, right? We just have 0 and 1 over here, we don't have any 1 star before that, right? So we'll have to retain that epsilon transition. Now to make the concept of epsilon NFA to DFA clear, let us also convert this to a DFA, so that we get all the concepts completely clear. So we have Q1, Q2, Q3 and Q4. We have 0, 1 and epsilon. So when Q1 gets 0, we have Q2. Since this is epsilon NFA, we'll have to write it in set form. When it gets 1, it doesn't go anywhere, and we have Q4. So let's fill this. Q2 when gets 0 is 5 again, and when Q2 gets 1, it goes to Q3, and epsilon, we don't have any transition. We have Q3 over here, so Q3 is doesn't have any transitions, so we'll have to write it with 5, denote it with 5. We have Q4 when gets 0 goes to Q3, and Q4 when gets 0 when gets 1 stays in Q4 and doesn't have any epsilon transitions. Now let us find E closures, since this is an epsilon NFA. So what is the E closure of Q1? So it is Q1 and Q4. So what is E closure? E closure is what transitions can we make without giving any symbol. So without giving any symbol from Q1, we can stay in Q1 as well. Also we can go to Q4, since epsilon is a special symbol that signifies that we do not need any symbol to make this transition. So this is the concept of e-closure. So Q2, e-closure of Q2 is again Q2 itself. E-closure of Q3 is Q3 again. E-closure of Q4 is Q4. Alright, now we'll convert this into a DFA. We'll convert this into DFA. So we'll have inputs as 0 and 1. In DFA we don't have epsilon symbol, anything like epsilon symbol in DFA, we know that. Now let us take, in this we have Q1 as initial state and we have Q3 as final state, right? Q3 as final state, right? Q3 as final state. So we'll take Q1. So what is the e-closure of Q1? E-closure of Q1 is Q1 Q4, right? So what is it? Q1 Q4? Yes. So Q1 Q4, we'll have to take Q1 Q4, and this is the initial state for this DFA. To find the results when 0 and 1 are given as input, we'll have to see what is the result for Q1 and Q4 over here. For Q1 it is Q2 and Q4 it is Q3, and check for the e-closure of Q2 here. So we have Q2 itself as e-closure for Q2, and for Q3 we have Q3 itself as e-closure, and we'll have to take the union of these two e-closures here. So we end up with finally Q2 comma Q3. Now for the input 1 we have phi and Q4, and again e-closure of Q4 is Q4 itself, and should I say the e-closure of phi will be again phi. It is obvious, right? Now let us take this state. So the main purpose of DFA is that every state in the DFA has is been clearly instructed which transition it should make when it gets any possible symbol. Here possible symbols are 0 and 1, so it should know where to go. So that's why we'll take one state at a time and define all the transitions. So we have Q2 Q3 over here as one state. So again let's see Q2 and Q3, we have phi over here. So again phi is e-closure of phi is phi again. We have 1 over here, Q3 and phi. So Q3 itself is the e-closure of Q3 and phi. So we have Q3 again. So now let us define for Q4. What is Q4? Q3, e-closure of Q3 again. So this is Q3. Again we have Q4 for input 1. So it's a self loop. Q4. Now we have Q3. Before that we'll also have to define what is it for, how should it behave when it is in phi. So phi is basically here a trap state, it doesn't go anywhere, so it will be phi again when it gets 0 or 1, right? And now let us take Q3. Now we have, let's check for Q3, it's again phi. So again enclosure of phi is phi again, and now we have defined for q3, we'll have to define for q4. We'll take q4 over here. So what is it? q3 for 0 and q4 for 1, and enclosure are also the same, so we'll just write q3 q4. Okay, q3 and q4, right? So we have addressed all the states in this transition table. Oh, have we defined q4 twice over here? So we do not need this row here. Okay, now let us simply name these states as A, B, C, D for simplicity directly. Now, so let us take A, and here we have final state as q3 over here, so we'll have to mark final state, the states as final state, all the states with q3. So here q2 q3 has q3, so we'll have to mark this as final state, and q3 over here also, so we'll have to mark this as final state. So B and D both are final states over here. Now let us take all the states A, B, C and D. So from A to B we have a transition with 0, and from A to C we have for 1. Wait, we'll also mark this also. Here also we'll just write the symbols, new symbols, so that it's phi will be phi, and we have q3, that is D again, q4 is C, and all these are phi. Alright, so this is 1, and from B we have to go to a trap state when 0 is given as input, and we have D, so B should have to go to D when it is given 1. And what about C? C should go to D when it is given 0, and should remain in C itself when it is given 1, and phi obviously in trap state it should remain there itself, and when D is given 0 or 1 it should go to trap state, right? 0 or 1. So here final states are C and D. Now here we have two final states. How do we now let us convert this into a regular expression using state elimination method. Oh wait, C is not the final state over here, right? B is the final state here. B and D is the final state over here. So now since trap state, from trap state there is no edge to other states over here, that is the main purpose of trap state. We'll just, it doesn't affect any other edges or relationship between any other node, right? So when we remove the trap state, we'll just have to remove all the edges that are connected to trap state. That's it. We'll not have to add any other edge to the automata. So we have this. That's it. Now we will remove the state C as well, since it is not a final state. So we have this, and we have D also, which is the final state as well. So we have B to D, that is 1, and also we have this route right through C. So what does it contribute? There's 1 over here and there's a loop here, so that is 1 star 0. So you can see that if we have A over here and a state over here and B and again a C over here, so from this state to this state we get the expression A B star C. So this is the concept. Now we have arrived at this expression as well. Now let us consider one state at a time as final state. So here we have two states, right? How do we convert this automata to a regular expression? Is that we consider one state at a time as final state and add both the expressions that we get from both the cases, right? So now for the first case we'll consider D as the final state. So we have A as initial state and D as final state. So we'll just have we know that we have 1 star 0, right? We also have 0 1, that is through the state B, right? So we have an expression 1 star 0 plus 0 1. So this is 1, and we also have 0 we have B as final state, right? Now in the second case we'll consider B as final state and eliminate the state D. So we have from A to B, that is 0. And do we have any other edge from D to B? No, right? So we'll have to just eliminate the edges that are connected with D and we'll not have to add any other edges. So the final expression for this will be, for this automata will be 0. Now we'll just have to add both of these expressions to get the final expression 1 star 0 plus 0 1. So what do we have here is this, right? We'll just arrange them a bit so that we can understand clearly. Here 0, right? And in this expression, what do we have as the most basic string in these two expressions? It is 0, right? And okay, it is 0, right? So there, since there is plus operator here, can we produce the expressions that these two produce from the expression 1 star 0? Let's see. So the basic expression from this expression is 1 0, right? 1 0. So is this expression produced from this? Yes, right? And the basic expression here is just 0. And can we produce that from this expression 1 star 0? Yes, when we have the value of star as 0, we'll produce the expression 0, right? So can we simply write this expression as 1 star 0? And now, is this the expression from which we created this final automata? Yes. So this is the expression that we use to find the automata from which we have derived this regular expression, right? So we have converted the given regular expression into a finite automata correctly, and also the reverse. So I hope this has given clear picture of how to convert regular expression to final automata and the vice versa, and also sub and also in the previous video we had used a formula instead of intuitively doing this, right? So if you have uh, trouble in remembering that formula, there's a simple derivation of that formula. So we have, if you know this derivation, you will easily remember the formula. So we can see that how I have named this R, S, T, U, right? It's in alphabetical order. Now since this T is the troublemaker here, because it seems that it is simply looping around, and how do we find the final expression for this? It will be very difficult if we simply do it intuitively. So now we can simply find an automata where this edge T is eliminated, right? So for that we'll simply assume that we have eliminated the state B here, right? So then we'll have this loop R, and also we'll have from S, from A to B we'll go through S, and we have a loop here U that contributes to U star, and again from B to A we come through T, right? So this is another loop on A, self loop on A, right? So we'll have to add that to R, add that with R, SU star T, and finally we will go to the final state where we'll not have to come back to the initial state A. So we'll simply have S and we'll have U. So if we now convert this into a regular expression, we have the loop here, self loop here, so we'll have to put this inside a bracket with the whole star, and finally we go from A to B with S and do some iterations with U over here, that's U star, and end terminate there. So here we have not lost the relationship T over here, but yet we have just simplified it so that we can easily express it in the form of regular expression. So I hope I have given the clear picture of the finite automata, converting it to regular expression and vice versa. Thank you for watching this video. Please subscribe to the channel and see you in the next video.